Okay, so now that we know that the planets orbit around the sun, and we talked briefly about having inferior and superior planets, so we know that some planets that are closer to the sun orbit faster, and those further from the sun orbit slower. That leads us right into Kepler. So Johannes Kepler set out to describe how the planets moved in their orbits, more specifically. And his research became known as the laws of planetary motion. Kepler has 3 laws of planetary motion, which simply describe how planets are moving around the sun in their orbits. So his 3 laws are the law of ellipses, the law of equal areas, and what's called the law of orbital harmony. So the law of ellipses. So all of the planets orbit the sun in elliptical orbits. Some get very, very close to being a perfect circle. But the Earth does not orbit the sun in a perfect circle, but close. So a perfect circle would be having what we call an eccentricity of 0. So eccentricity is the way that we talk about how elliptical an orbit is. So an eccentricity that is very close to 1 means the orbit is very elliptical. An eccentricity that is 0 means the orbit is a perfect circle. So an eccentricity of, let's say, 0.05 is close to a circle, but not quite. And that's where most of the planets lie. Now notice, if you had an eccentricity of 1, you would have a straight line and no longer have an orbit or an ellipse. So his first law is simply stating that the sun sits at one focus, and there's nothing at the second focus of an ellipse. The sun sits at one focus and the planets orbit that sun in an elliptical orbit. The second law is called the law of equal areas. So here's a picture of our sun with a very elliptical orbit, a planet orbiting a very elliptical orbit. So if you drew a line from a planet to the sun, it would sweep out equal areas in equal intervals of time. And this is because the orbital speeds are not uniform, but they change in a regular way. The orbital speed increases as the planet is close to the sun and decreases as it's further. So therefore, if you were looking to see how much area the planet swept out between points C and D, that planet would be moving very fast. If you looked at the points A and B, the planet would be moving slow, so it wouldn't go as far around the orbit, but of course it's further from the sun. So if you added up the areas underneath those red areas there, you'd find out they're equal. And that's just due to how quickly the planet is moving around the sun. So closer to the sun, it's moving quicker, and further from the sun, it's moving slower. His third law just talks more specifically about how the orbit, how long it takes to orbit, is proportional to the distance. So we call how long it takes for a planet to orbit the sun its period. The period is in years, typically, Earth years. So that's how long it takes the planet to go around the sun. And we call this period, we note this period with a capital P. So the period, or how long it takes to orbit the sun, is proportional to how far away the planet is from the sun. We represent that distance as lowercase d, also called the semi-major axis of the ellipse, and we measure this in astronomical units. So for any planet, the square of the orbital period in years is proportional to the cube of the planet's average distance from the sun. So this is just a relation showing how quickly the planet moves around the sun is proportional to how far away it is by the square of the period in the cube of the distance. You can check out the video down there for a little bit more on Kepler's law by Carl Sagan. Now, in addition to Kepler, Galileo in the late 1500s made some observational discoveries with his telescope, which really helped solidify the heliocentric view. So a few of Galileo's discoveries were Jupiter has 4 large moons. He discovered that planets are actually circular disks and not points of light. And especially important, he noticed that Venus exhibits phases just like the moon does. This proved that Venus does in fact orbit the sun. So these were crucial. So it wasn't that Galileo invented the telescope. It was the fact that Galileo was able to use the telescope, which was not invented yet before his time, to make these major discoveries which helped solidify the heliocentric model. This dives us into Isaac Newton. So Newton has his laws of motion for the physical world that we live in. And these are formed through experimental observation. Now what's important is that Newton showed that Kepler's laws of planetary motion followed directly from his laws of basic motion in the physical world. So this links these two laws of motion together. So let's look at Newton's three main laws of motion. You can think about how they might compare to Kepler's three laws of motion. So before we start, let's just think about some key concepts that are going to be important for you to understand Newton's three laws of motion. First, there's this concept of force. Force is a push or a pull, an agent of change. So an object needs something to get it moving, and this something is usually a force. So an object is going to stay at rest unless something is acted upon it. So a book is going to sit there on the table unless you push on it, and that push is the force used to get the book moving. Now, in the same way, an object that is moving needs something to cause it to stop moving or change direction, and again, that something is a force. So we have things like the force of friction, which retards the motion of something moving, so like the friction of the road on your tires. We have gravity, the force of gravity, which is the downward pull attracting the planets to the sun, the moon to the earth, and you to the earth. So we think of these as all types of forces. So forces have units called newtons. And a force may be balanced or canceled out by one or more other forces. And if that's the case, there's going to be no change in motion. So the book is sitting there on your table and not moving because the forces upon it are balanced. If the forces are not balanced, that's when motion occurs. And we call this a net force. So an example would be the game of tug of war. So when the tug of war, both sides are balanced, meaning they both have equal forces pulling on both directions, there's no motion of the tug of war game. But as soon as one team applies more force in a direction, you have a net force, and in the image, it's to the right. And that means the rope and the players are going to move in that direction. So you have an unbalance of forces causing them to move. So the force is integral to Newton's laws of motion. So let's talk about his first law. An object remains at rest or moves in a straight line at a constant speed unless acted upon by a net outside force. We call this the law of inertia. It's the resistance to change in motion. So the picture here of this bicycle is a perfect example of inertia. And the little caption there says, inertia, you lose. So the man was riding on his bicycle and they both had a motion moving forward. But the bicycle wheel stops, but the man still has the motion moving forward and there's nothing to stop him until he hits the ground. And this is what we call inertia. He continues moving unless a force is acted upon him. So he's going to continue moving forward because he was moving forward on the bicycle. He will eventually stop, of course, when the ground applies a force to him. So with inertia, mass is essential. So the greater the mass, the greater the inertia. And therefore the greater the resistance to the change in motion. So please watch these two videos. They're great examples of inertia. Keeping your seatbelt on is fundamental, otherwise inertia is what's going to cause you to fly through the windshield in an accident. I also love this other video I have about an astronaut in space. Space where there's nothing to act upon an object, once it's pushed in the vacuum of space, continues to keep moving. So you'll see in this video the astronaut did not tie down the tool bag that she's working with, and the tools continue to move because she gave them a push in one direction, and because it has inertia, nothing is going to stop it from moving. So please watch these two videos. They're great examples of Newton's first law of motion. and a little comic just for fun. So his second law of motion describes the motion of an object and how it changes if there is a net force acting on it. So now we're going to talk about a force acting on it. So the force is equal to the mass of that object times the acceleration. So for a body at constant mass, the larger the net external force, the larger the acceleration. So for any kind of object undergoing a constant acceleration, the larger the mass, the larger the force is needed. So just think about it this way. If you want to change the motion of an object, I could move my book, okay, give it some acceleration without a lot of force, because it's not very massive. But if I want to move a semi-truck and change its acceleration, I have to apply quite a bit of force for that to happen. And his third law is especially important to studying space in terms of rockets and talking about how we move around in space. Newton's third law, or you can think of it as symmetry, is very simple. For every action, there is an equal and opposite reaction. And this is what makes rockets go up. You have a force pushing down and the rocket is moving up. You can also think about if you blow up a balloon. If you blow up a balloon, you're pushing air into it, and then you let it go. Your air is rushing out of the balloon, but the balloon moves in the opposite direction. That's what Newton's third law is all about symmetry. So another good example is firing a gun. The bullet is shot forward, but that reaction force hitting your shoulder is the opposite reaction. So every force, there's an equal and opposite force in the opposite direction. So whenever one object exerts a force on the second object exerts an equal force in the exact opposite direction. Finally, we have the law of universal gravitation. So every object or every body in the universe attracts every other object with a force that is directly proportional to the mass and inversely proportional to the square of the distance between them. So this means the closer you're getting, the more you're going to feel that gravitational pull. And the bigger you are, the more you're going to feel that gravitational pull, based on the inverse proportion of the square of the distance between them. So gravitational force decreases with distance, and the greater the mass, the greater the gravitational force. So planets have elliptical orbits. This came out of this idea of universal gravitation, just like Kepler said. Keep in mind too, when we talk about mass, that's different than we talk about weight. So when we talk about your weight, that is due to the gravitational acceleration or force on the Earth. Mass is simply what you are made up of. Your weight is how much your mass being pulled down by the gravitational pull of the Earth. So there is a difference between mass and weight. Please watch this video. It's a little old school, but it talks a little bit about orbital mechanics and the application of Kepler's and Newton's laws. So watch it, but go ahead and stop watching at minute 9. Otherwise, it gets into much too technical detail. Another great result of this gravitational play of the Earth, the Moon, and the Sun is our tides. So because the Moon has a gravitational pull on the Earth, and the Earth has a gravitational pull on the Moon, we can affect each other. And what's neat about our Earth is our oceans are fluid and dynamic. They can move around. So our oceans feel the tug from the Moon and from the Sun. And this causes the tides. So when the Moon and the Sun are in a line, that's when we have our largest tides, called the spring tides. When the Moon is at a 90-degree angle to the Sun, meaning they're not pulling as strongly with each other, we have the low tides called the neap tides. And this is just due to the pull of gravity of both of these objects on our Earth. And the oceans are malleable, they can move, and therefore are affected, resulting in the tides.